Hey guys, 2009 exam. I'm gonna go have a look at electronics. Just let me move some things out of the way. Okay, let's do it. So, this is the reading time part, but we'll just be reading this. This is a circuit. Have a look at it. It's pretty simple. That information's all here. What is the potential difference of voltage drop across R2? Which is how much voltage drops across there. Which formula would we use? Well, we're trying to find how much voltage drop is across one resistor as opposed to the whole circuit. So, that's pretty much the voltage divider formula. We're trying to divide, we're trying to get one voltage out of the whole thing, or like divide one out of everything. And here we get R, we want it across R2, so that's 30 ohms. And divided by the R total, which is 30 plus 40, which makes 70 ohms, times V in, 10. So it becomes 30 on 70 times 10. Easy. What is the power dissipated in R1? Power dissipation is, well, we have voltage and we have resistance, so we can just use our power rule in terms of power equals V squared on R. Simple. Now add a third resistor, 20 ohms. So how do we find the current through the ammeter A now? It'd be different from before, because this resistance has changed. We use our parallel resistance formulas, this one, to figure out what the resistance should be, and just having a quick look. I did it before actually. That'll be 13.3 ohms. So our total resistance is 43.3 ohms, and then we can use current equals voltage over resistance. I did this in the cheat sheet section when we were doing revisions, but I'll have a quick look for you now. Have a look at it. So ignore all these little numbers. Essentially, we know this is a LED. And just because of the graph, we know something special happens at 3 volts. Okay, this is how much each LED takes up. So to figure out what the value of the current through R2 is, we have to realize that each of these LEDs, some people would think to do 12 volts divided by the resistance, and then use current equals V on R. But they'd be forgetting that each of these takes up 3 volts. So this takes up an entire of 9 volts. So we only have 3 volts left for this. And I also want to point out that this takes up 9 volts and this takes up 9 volts. They both don't take up 18 volts. It's just that 9 volts goes this way because half the current goes down, half the current goes this way. So still here to here it will be 9 volts. Okay, so we can figure out 3 volts, 60 ohms, V on R gives us current. This one, if we reverse one of the LEDs, we know that they don't conduct, like no current goes through if it's reversed. So that means the current will easily go through here, that still works, but the current going through here all gets blocked off and none of these will work. All 3 of them are off. So this is an amplifier. What is the voltage gain? In the linear region, voltage gain is V out over V in, or the gradient, and that's 9 volts over 30 millivolts. Well, it's minus 9 volts over 30 millivolts. So to convert it becomes 9,000 volts over 30 millivolts. 9,000 millivolts over 30 millivolts. And we just divide it. And that's pretty easy. Input signal. So sketch the output signal of the amplifier and associate a scale to the vertical axis. So the key things we need to know about the amplifier is first its gain. So we already had that from before. Is it inverted? What's the upper, well, these are things, but inversion and clipping are the most important in drawing it. So it is inverted. Okay? So if it's inverted, our diagram is going to go upside down. Is it going to get clipped? So we have an input voltage of minus 50 millivolts. Yep, that does get clipped. It can only go up to 30. Okay? And the max voltage is 9. Okay. So we're going to get clipped at 30. It's going to be like that. So far, it's going to be upside down, getting clipped like that. You see? because it's inverted, and at 30 it gets clipped. Now, the max voltage is also 9 volts, so that tells us, because we were drawing this, but we didn't know what numbers to put on the scale. That's the last part we need, so we just put 9 volts there. So, sorry, we draw it this way. It's inverted, it's clipped, and the max is 9 volts. Good. Alright, this question. So just have a quick look. I'll try and refocus it. Okay. This is a schematic of modulated radio signal. So we need to label P, Q, R, and S with these. So first of all, we can look at our modulation. We know the input signal looks like that. The carrier wave is like that. That's the code. Okay, this is our message, this is the code. And then we put them together to get a modulated wave. What's the wave that's modulated? Oh, that's kind of like the encrypted message. Okay, if that makes sense. The code, now this is our message, this is the code, and this is how we encrypt it. That's kind of what modulation is. That's an analogy that I understand, at least. So we send our message, we stick it with a code, we encrypt it, and it comes like some message that no one can read, and then we unencrypt it to get S, to get our original message. So, P is B, which is our message, or input signal. Q is A, which is our carrier wave, because this is what carries the message across. R is C, because this is our modulated wave. This is when we combine these two. And S, we undo everything, and we get back our original input, B. This page is blank. You didn't see me nod. I was pretty happy with a blank page in an exam. Okay, temperature resistant characteristic of a thermostat shown in figure 10. What is the resistance of the thermostat when temperature is 5 degrees? Easy, we just read it off the graph. 5 degrees, 5,000 ohms of resistance. Now we have a circuit. So all this is going to explain this. Just read it, and then I'll talk about the important points. Okay. Switches on when there's 8 volts here. Switches off when there's 8 volts here. When it goes below 8 volts. This is our thermistor, that's the resistance, and this is the variable resistor that we get to decide upon. Oh joy! The air conditioner needs to come on when the temperature rises 25 degrees. What resistance should the variable R be? So maybe you don't know what you're doing in the exam, but you know this, 25 degrees. There's only one way to use this piece of information, and that's to go here and say 25 degrees. That means 500 ohms of resistance. So I can replace that with 500 ohms. I need to figure out what this is, and I know there's an 8 volt difference across here. So this is 500 ohms, that's 8 volts. I know this is 12 volts. So the voltage difference across our thermistor must be 4 volts, 8 minus 4. So this would be 500 ohms, 4 volts, this is 8 volts. And therefore we know the resistance, since the resistance is proportional to the voltage. This resistance has to be double that, because the voltage drop 8 is double 4. This is double that. This is double 500, this is 1000. And the air conditioner now needs to come on at a lower temperature. Should the variable resistor R be increased or decreased to achieve this? So we'll go back to here. Remember, lower temperature. So at a lower temperature, we realize this resistance rises. So this resistance will rise. So to keep the same proportion of 4 to 8, or 4 to 8 here, if this rises, this variable resistor also has to rise. And I think that is all of electronics for 2009. Awesome. That's pretty much all the questions. We'll catch you later. Have a nice night.